Hello everyone and welcome to the Autodesk Robot structural analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to take yet another look on another aspect on dynamic analysis called time history analysis. Now this is something really interesting because in time history analysis, you are able to basically define a force and describe the variations that the force undergoes in real time. So to do that, I'm going to open my 3D building design. And before I start, a quick shout out to my dear subscribers, Donald Honey and Ni Sapai, for their amazing insights and comments. I have read them all, and I will just be touching about some of those comments. However, there are future videos to basically explain and deal with all the aspects of their comments. So a huge shout out to them both. Thank you very much. You're really helping me, and you're also shaping the future videos of this channel. So thank you very much. And of course, if you, dear viewer and dear listener, want to also take a part in suggesting videos and being part of this community that is actually growing right now, I of course highly recommend that you usually subscribe and try leave a comment. I usually read them all and I reply to them all as soon as I can. In this video, as per our tradition, we are going to basically have two structures. The first structure is going to be a simple column, a cantilever column, just to explain the basics of the dynamic analysis. Then I'll be talking about the structure just to see how structures perform with that regard. All right, so to start with, I'm going to basically make me a quick column, and we have the structure right now, so let's do that very quickly. I'm going to use the same reinforced concrete column, 350 by 700, and I'm going to basically define me the reinforced concrete column here. Of course, to do that, to be able to analyze that, I need to apply me a fixed support this time. So, okay, we have a fixed support now. The following, of course, is going to be following the same steps as the previous video, which is the model analysis. So I'll quickly video edit this, and well, let's video edit. Okay, so basically by the power of video editing, we have a 7-story column. Now, I highly recommend that you watch the previous video called Model Analysis in Robot before you start this, because it builds upon the previous knowledge that we have gained there. I'm just going to open me here a dead load case. This time I will delete the self weight because I don't want any P delta effects to be taken into account here. Of course, I never talked about P delta effects and nonlinear analysis. This is of course a very juicy and nice topic that I will be leaving for later. It's really amazing what Autodesk Robot can do, and it's also really amazing, to be honest, what structural engineering has in store for you. I'm really glad that I am a PhD holder in structural engineering. It's such an amazing world. All right, so I'll just go to my node force. I'll apply me, I don't know, like 5 kilonewtons in the x-axis. Let me make sure what axis I'm applying to. Okay, it's a strong axis, so 5 kilonewtons in the strong axis. All right, so far so good. Now I'm gonna basically go to my analysis types, define me a model type, because it's basically the quest that opens everything else. I'll just define me a model type, and I'll leave it as 10 modes because I've talked about this before. That's not my point now. So I basically click OK now, and now I'm gonna make me a new type of analysis, and this is where the new stuff starts. If you click on new, well, I've talked about harmonic last time, so let's take a look on time history analysis this time. So let's apply that. When you click on OK on time history, suddenly you are greeted with this huge thing of a time history analysis definition. Now, first of all, there is something called the method. Now, you need to know that a dynamic analysis contains of solving the differential equation that is mass multiplied by acceleration plus speed or velocity multiplied by damping and distance multiplied by stiffness equals force. Now, this differential equation is solved in structural analysis softwares using a plethora of possible solution methods. The best one is Newmark's method by far. This is what the scientists, at least in my opinion, what I use when I want to do a analysis of structures to perform a time domain analysis. Now, of course, for the dynamics specialist here, they do know that we also have the ability to perform a model analysis using the orthogonality of modes, and this is something I will leave for you, dear viewer, to think about. This analysis using the mode shapes is basically called model decomposition. Of course, there is much more than this, but I'll basically go to Newmark's method, the time step method. If you click on Newmark's method, it asks you about the time step. The smaller the time step, the better. The division and your end time, basically like how many seconds do you want the analysis to run. Now for me, I'll let it run, I don't know, 30 seconds. Please notice that any second you increase on this analysis will increase the calculation effort. So now here you can see that you have a time axis and a value axis. This time value graph is basically the graph of your force. What's the f of t? What's the variation of the force with time? Now you don't have anything here, and you can basically not click any function because you have not defined any function. So how do you do that? Well, first of all, what you're defining here is a factor versus time. So the loads that are defined are going to be multiplied by a factor. Now the question is, what kind of loads are going to be multiplied by the factor? The kind of loads are going to be multiplied by the factor are basically the loads inside the dead load. If you have other cases like live load or whatever loads, then you can select them to be selected. This is different from harmonic because when you define harmonic, like in the previous video, you have to define the forces inside the harmonic case. Time history is different, as in it defines the function of time and the function of factor, and this factor is applied to a different case, meaning all the loads in that case get variated dynamically. What we are going to do is basically we're going to click on the function definition button like this, and in this case you can basically define a function. Because there is no function here to add, in this case we need to define our own function. So for example, here I can say my function as the name of the function, and I can add that, and in that case I can start defining the function. Now a function can be defined by a variety of points or even functions. But a robot allows you to define basically functions of functions, like you can define one single function and you can add those functions together by summing them up, for example. So you can have multiple functions here, and then you can create a function based on those functions. Now allow me to show you how a function looks like. It's basically a number of points, and the points here have a time and an f of t, which is the force factor of at that time. So for example, at time t, I can say that there is no force, and at time, for example, 3, I can say that, or let's say at time 1, I can say that there is a force, 100% force. So you have a linear increase. For example, I can leave this force for 3 seconds, and then I can eliminate the force at the 5th second, as you can see, by zeroing the force. I can also reverse this process by, for example, reversing this at second number 6, and putting a -1 here. So now you can see that my force is being reversed. And I can keep this force reversed for yet another 3 seconds by going, for example, to 9. And then I can zero the force, repeating the cycle yet again. So if at 10 seconds, I would say I have a force factor of 0. So now I have my full cycle. You can see that this is some sort. Now this is not a sinusoid, this is not a sine function, but I mean I'm just trying to make me a little force application, force removal, force reversion, and then force removal. So you can see that we have some sort of little semi-sine. It's not a sine, of course, but I mean it's just a try. So if you add that, or basically close right now, this gets saved in my function, and you can select this my function and you can add it, and you can see that the function value gets added. Of course, my guess is, I'm not really sure, I need to check that, but my guess is that the force keeps repeating until the time ends, but I don't know exactly. I have to try that, to be honest. So I'll just click on OK right now, so I have it. And well, let's calculate that thing. Now, if you perform your calculations, you can see it takes a lot of time because Numarx is used to calculate 3001 steps, because your time step is 0.1 and the division of the time step is 10. So you have, and your time is 30. So 30 divided by 0.10 is 300, multiplied by 10 is 3000, which takes some time. And this is a very simple structure. You can imagine how ridiculously much you need for a long or bigger structure. All right, so I select dead load once again to open the deflection shape. It's 157.3. I think this is the same as the last time. If you go to model, of course, you don't see deflections. You see mode shapes, but you need to select the correct mode. So mode 1 is 0.22. It's in the y-axis. And mode 2 was in the x-axis, I think. Let me just check. Yep, it's at the x-axis at frequency 0.44 hertz. I want to keep this number in my head because I will be using this in a moment when I apply my forces. So this number is very important because I'm going to try show you or try to create a time history that is or mimics a harmonic. Now it's not going to be perfect, but well, at least we can try. The new stuff of today is basically your test. You have test plus and test negative, which is the envelope, but I'm more interested in test. When you open test, you can open also the forces, and well, let's take a look on what we have here. Okay, so if you click on test, you don't see any forces. This is rather odd, and of course, you need to show the deflection shape just to make sense of it. Now, if you click on forces, nothing happens. Why is that? Well, it turns out because sadly or unfortunately, we were in the time point where there was no force. Now let's take a look on this. See, if you scroll through this, you can see the force increasing. I mean, take a look. I'm using the arrow keys to cycle through the time variables or the time steps. So while I'm moving to the right side, you can see that the time increases zero point 0.5. And you can see that my force is increasing, keeping for 3 seconds, and you can see the structure is vibrating now, which is amazing. Like you can see all the structural dynamics happening here. The force dies, which means the structure swings back and then is held in place with the other force. And then it dies again, the force dies again, and you can see that the structure swings back into place. Oh, and just to make sure that you understand this, the force will not keep repeating. Your analysis is 30 seconds, but the force was only applied for 10 seconds, and this means that the structure will keep vibrating. Now, I think there is no damping based on my little expert eye. I think damping is not included. Let me just check. I'll just basically start an animation and take a look on that because I want to see if damping is included or not. I personally do not think that damping is there. I cannot see any exponential decay of the motion. Let's see. So from here to here. Yeah, no, it's not decaying. Okay. Yeah, see, I'm holding my cursor intentionally in a certain position, and you can see. I mean, look at the deflection; it's still 175 all the time. So no, I don't think there is a damping here. But well, let's just wait until this finishes. I'll basically video edit this right now. So why is it not damped? I think I didn't apply any damping. So well, let's apply some damping. Okay, so how can I apply damping? Well, of course, this is really, really deep now. But you go to basically your test, and you modify your parameters basically, and you can see that you have here a button called damping. If you click on that, oh yeah, there it is. So the alpha and beta dampings are not defined, thus you have no damping. Now, how do you define alpha and beta? You either calculate them from modal damping or just assume values based on what you see in structures. And you can actually calculate alpha and beta from the modal damping. For example, you can assume that for the first mode you have a damping of 5%, and the second mode you have a damping of 5% if you want. Now, of course, you need to calculate omega, which is the radial frequency based from the normal frequency hertz. And to do that, you need to understand that, well, 1 hertz is 1 full cycle, and 1 hertz means 1 full cycle per second, which means 2 pi radian per second. Now, for example, if you have 0.44, you just multiply this by 2 pi and you get your radian, or just use this calculator. So I'll copy that very quickly and take it to my robot and basically apply that. So I apply that paste. You can have a damping for 2 modes if you want, but you just click on calculate and it gives you your first mode damping alpha. If you add another mode, you can have it another damping. For example, let me just here put a dummy value of 7, for example, and you can see now that you have alpha and beta. I'll keep that like this and click OK. So now we have damping applied. Now this is extremely important that you understand and read about modal damping and of course the shortcomings of damping, because the entire damping thing is kind of strange. To try to intrigue you, we assume that structures dampen by assuming that the model for damping is a viscous damper. Meaning, for example, if you take a stick and move it in water, you know that you are being resisted. If you take a stick and move it in water, your movement is resisted, and the faster you move, the more resistance you face. Now, this is somehow similar to what our assumption to damping is. As a matter of fact, we say in our dynamics equation, we say that it's actually c multiplied by v, or damping multiplied by velocity. So there's a lot of shortcomings there. It's really a simplification, and that's the best thing we can do right now. Okay, so I'll just click on OK right now and repeat the analysis. So let's take a look, and you can see that this is really amazing. I mean, now I have to wait again, hoping that my structure is damping. So, well, I'm just going to wait very quickly for this to finish and take a look on the results. Intentionally, I'm not basically cutting this because I want you to see that, well, those dynamic analysis do take time. So, okay, well, I'm just going to create an animation right away. Okay, so I think it took me too much time to wait, so I'm just showing you the intermediate results now. You can see that, yes, the structure is damping because it's not swinging back and forth very widely. I mean, take a look when the force dies right now. So when the force dies, which will happen in a moment, you can see that the structure actually vibrates back and forth, but you can see that with each passing vibration, the vibration dies down. So if you take at the mouse position here, the vibration is now not reaching the mouse position. If I go back with it, you can see that in the next cycle, the vibration will not reach the mouse position, and so on and so on. So what ends up happening is the vibration dies down because of damping. And yeah, well, that's exactly what I wanted to see. So now we have applied damping to our little column structure. But that's not all, because there is more where that came from. Now, one thing I'm interested in is to see if I can simulate modal analysis using time history. So my frequency is 0.44 hertz, meaning that I have 0.44 vibrations per second. So I want to invert that to see the time of force application. So let's take a look. I'm going to say 1 divided by 0.44, and well, I have 2.27 seconds, meaning that I should apply a force at intervals of 2.27 in order to create resonance. It's not going to be perfect when I do that, but I'm interested in seeing what happens if I do that, because I mean, it intrigues me and I kind of enjoy that. So if I go to parameters right now, Autodesk Robot actually had a bug, and it took me far too much more time than I really want to admit to do, but well, I tried my best to simulate what happens if we pulsate a force using time history. So for some reason in Robot, my definition for time history stopped, how can I say this, cooperating. So I thought, okay, well, let's give it an initial shove, like an initial pulse at 0 seconds with a full brunt of force. And then basically we'll start pulsating the forces each 2.27 seconds. Because on the x-axis, the frequency was 0.44 hertz. So 1 divided by 0.44 equals 2.27. So you can see that here I have at 3.27, at 5.54, and at 7.81. So basically those pulses are 2.27 seconds spaced. The first pulse is spaced incorrectly, but it took me far too much time to do that. So due to a certain bug in my robot application, so I'm not going to do that. I'll just keep it like this. Anyway, I'm interested in seeing the effect of simulating pulses on the time history of the structure. So let's take a look. Now, for the dead load was 157, so I really don't have any idea if it's working for the seismic or time history or not. An important thing to note is that I've removed all kinds of damping in the time history analysis because, based on theory, and this is really technical now, damping affects the natural frequencies of a structure. So I had to remove it to make sure that the natural frequencies actually are preserved. And I'm running my analysis hoping for the best. So let's take a look on the results of that analysis. My time history this time is 10 seconds only, so let's take a look and I don't know, just look what happens. And I hope, it seems working. Okay, okay, this is promising. You know what? I'll let the animation talk for itself. So here is your 10 frames per second. Oh, look at that. This is lovely. I need to stop. I need to show you this in full. I need to show this in full glory. So give me a second. Now this is some really golden stuff. So okay, let me just rephrase what I have done here. I tried multiple times because it took me really a lot of time here. And just to remind you that my model analysis gave me a second mode or the first mode in X to have 0.44 hertz, meaning one vibration each 2.27 seconds. So now I've modified my time history to apply a pulse each 2.27 seconds. So let's take a look if it worked or not. So to see that, I'll just show you very quickly the time history in an animation. And I think it's working because take a look, the dead load has 157, which is a non-vibrating force. Anything beyond that means that we are touching on the modal characteristics and on the resonance of the structure. So, well, let's just animate the thing. And I'm going to use 10 frames per second because my time history was at 0.1, meaning that each 10 frames represent 1 second. Oh, look at this. Look at this amazing stuff. I'm basically in love with this. So take a look. The first pulse, the second pulse increases, the third pulse increases the structure, and you can see it's building up. Each pulse increases the deformation. So once again, the first pulse, the second pulse was mistimed. but the third pulse is perfect and the fourth pulse is perfect. You can see that each pulse of force happens when the structure is at its very beginning here. Right now, take a look. Now here, force pulsates again, force pulsates again. So you can see that the force pulsates exactly on the same time, except for the first time. I told you that my first pulsation was off, and I didn't want to repeat that and improve that because it took me so much time to work through the bugs in Autodesk Robot. So take a look now. See, now the force is applied when it reached the maximum. And now the force is applied when it reached the maximum. You can see that because the force pulsates exactly at the adequate time, you can see that the displacements build up, which is basic resonance. This is what happens when you use harmonics at 0.44. This is exactly what happens, but harmonics are basically a repetition of the force to infinity. Okay, so this is how a force in on a column looks like. So well, let's video edit a full structure in this. So okay, give me a second. Okay, so now I have a structure that is loaded 5 kilonewtons on the top floor. Now, this might not cause a resonance because the frequency of a structure is different than the frequency of a cantilever beam. Let's take a look what happens when I do that. So I run the analysis right now. It starts calculating the model frequencies, and also it starts calculating the time history. So, well, it takes some time to calculate, especially because we are dealing with a big structure. So, well, you can see the difference in calculation time between a cantilever, or basically a cantilever column, and a full structure. Anyway, okay, so our analysis is complete, and before I start talking about the time history, our dear subscriber Nisapai has asked a question about the mode shapes. Also, our dear subscriber Donald Hani has requested to explain the vibration of machinery on structures. And yes, vibration of machinery on structures creates a centrifugal force that could vibrate the structure in its resonance. Now, due to problems I faced with Robot in time history this time, I think I will uninstall it right now. But after I finish this video, of course, I am unable to do this. I'm not risking again to have the same bug because it took me, I don't know, like 1.5 hours to fix just to be able to record this video. So I will shift our dear subscriber Donald Hania's question for later. However, since this is working, I can address the question of our dear subscriber Nisapai. Now, our subscriber has a problem by basically the first three modes seem to make sense, but the other modes don't. So now this is a different structure from last time, but I will analyze it anyway. So the first mode is the mode of vibration of the columns in the weak axis. So yeah, of course, we are expecting the weak axis to be easily to be bent. The second mode is twisting. There is absolutely no problem with that. The third mode is the strong axis bending, which makes sense. Now, please notice that any other higher modes will make less and less sense and are actually really hard to excite using forces. But well, let's take a look. So, also, the variation of a structure is usually a mix of all modes. So let's go to mode number 4. Mode number 4 here seems to be the second mode in the weak axis, which I think makes sense. Okay. Mode 5 is some sort of second order twisting or something. It seems that my structure is stretching in the diagonal, which is, I don't know, it looks like a spider web. I'm totally not happy with this, and I would accept this. I would not accept this as a feasible mode of vibration. But well, let's take a look. Now, mode 6 is a. I think this is the second twisting mode. You can see the structure twists twice, I think. So yeah, I think this is the second twisting mode. We are reaching the second modes now. The mode 7 is the second mode. Now, this is really strange. And this is where things become a little bit iffy, especially for our subscribers. So you can see that the modal calculation resulted in a structure where the first and second layers of columns bend in the strong axis to the left, and those two bend in the strong axis in the left, and the rest bends in the right. So the strange thing here is it seems that the calculation resulted, or from the calculations we can realize that the structure is strangely easily to be bent double in the strong axis rather than the weak axis, which is counterintuitive. The reason why this is happening is because your beam is long, which means the stiffness of the beam is really low, and you can notice that in the first and second mode here. Let me show you here. In mode number 1, which is here, you can see that no beams are bent. The beams are perfectly linear, and thus the stiffness of the beams is not taken into account, and that's why This is the first mode. There is no stiffness for beams. You can see beams are perfectly fine. Also for this one, mode 2, you can see that my beams are almost perfectly fine, linear. The only things that bend around are the columns. Mode 3, same thing. Beams are not bent. You can see that mode 4, even for mode 4, the beams are slightly bent. So the stiffness of beams is really not a factor in this calculation. If you go to mode 5, this is where beams start to deform slightly more visible, and it becomes greatly visible for mode 7, where the beams have to be bent. You see, now uh, the structure for this mode has to bend the columns in its strong axis and bend the beams along their longitudinal axis. It seems that this mode is easier to achieve than this mode. Let me just search for it because I want to show you this. Give me a second. I'm trying to find it. I think this one. See, this is the second mode where the the columns are bent on their weak axis, but this is a higher level mode. You know, this seems higher mode means it's a harder mode to achieve, like mode 7. Look at this. Mode 7 is strangely in the strong axis of the columns, but it seems to be easier achievable. It's 5.34 hertz when compared to mode 13. Although mode 13 bends the columns on the weak axis. And this is, I think, if I'm reading the thoughts of my dear subscriber correctly, this might be the thought why our dear subscriber Nisapai had a problem with this. Now, the truth to be told, it's not only the columns that are being bent, it's also the beams that are being bent. And you can see that this beam is much shorter than this beam. This beam is like 1.5 or 1.6 times longer than this beam. And you know that stiffnesses have to do not with lengths, but with length square and length cube sometimes, and even higher values of length. So the idea here is that yes, the column itself is easy to bend in this direction, but the beams are not. And a beam that is long is easier to be bent than a beam that is short. Now, the sorting of the modes is not exactly similar to the previous structure, but my conclusions still remain the same. Now, the rest of the modes are basically some strange garbled mess. I mean, what are we even looking here? Like, this is what the second mode of I think this is the second mode of the beam in the horizontal direction, coupled with the column in the strong axis. And well, it just gets a garbled mess. Like this is the third mode in the vertical. You can see that this mode is achievable because the beams are not being bent. Well, if we go to mode 16, you can see that the beams start to be bent. You see, when you bend beams, things get harder to achieve. Of course, I mean, what are we even looking here? This is 9.66 hertz. Please notice a very important thing. I think I missed to say last time. We are talking about hertzes here. Like 4.53 hertz means a force that hits the structure 4 times per second. Now, yes, I know that machinery is capable of producing 50 and 100 hertz. Yes, you need to check this out with machinery, to be honest, and I need to make a video for this, but not today. However, what I want to focus right now is that usually not only is it machinery that causes our structures to vibrate, it's actually earthquakes. I'm talking about most of our structures right now, most of our residential structures. And when it is earthquakes, you can see that earthquakes, I mean, seldomly have a 3 hertz vibration for earthquakes. And even if we have a 3 hertz vibration earthquake, those are rather short and would not be long enough to actually cause some serious problems with resonance. Notice that it's a long story about energy that is imparted by earthquakes, which has to do with frequency and like amplitude. It's a long story and really theoretical here. I only want to just give you some nuggets of information, and well, I'll leave you intrigued enough to check it out yourself. You need, just as our dear subscriber Donald Tanya has done, which I would like to extend my thanks to. He just gave it a quick dive to take a look, and well, I think if you do that, my dear listener and subscriber, you could learn something new. Anyway, uh, before I finish, I want to show you the time history of the structure. It's gonna be nice. Wow, really? Are we resonating? Let me just check that. I don't know if we're resonating or not. Okay, so what was the model analysis? Let's take a look. I just want to check something. 1.85. Is it a multiplier of 0.44? Let me just check something. So 1.85 divided by 0.44. I'm testing a hypothesis here. 4.2. Okay, so it seems to be a higher harmonics of this. Maybe we have a resonance here, but a higher harmonics resonance. This is extremely technical. Like, I need to explain this to you in painstaking detail. Higher harmonics means that you are swinging your brother, but you are applying a force not every time. You are applying a force, your brother comes back, you don't apply a force, your brother comes back again, and then you apply a force. Like, you are applying a force, and then not applying a force, and then applying a force. Like, you have a gap. This is called higher harmonics because you are applying or imparting a force each second cycle. Now I just checked the mode of our structure here is a 1.85, which is almost 4.2 times the 0.44 hertz, which means that we might be enticing or exciting a higher harmonic here. Now I don't know. It needs to be checked. Of course, this is PhD stuff. So I don't know. Let's try that. So let's make some sort of animation to take a look on the structure. This is a funny structure. This is a really funny structure. I don't know what I'm seeing here, to be honest. I'm really surprised. It seems that our beams are really vibrating a lot. Okay, let's take a look. So, okay, so before I start doing this animation, I should basically go to my design to my results, diagrams and numbers, and normalize just to make sure that we are on the same page here, and that we are on deformation and normalize, just to make sure that we are not like overreacting to any sort of basically deformation. I am sensing some vertical forces here. Now, of course, you can see that the structure vibrates much more and much more violent because the frequency is higher, so obviously the structure vibrates much higher. You see, the more stiffness you have, the faster you vibrate, and because the structure has a strong stiffness, it's vibrating immensely. And don't be like put off by this strange yo-yo movement. Notice that we are talking about 5 millimeters. We are talking about nothing here. But because our displacement is small, every displacement gets amplified, and you can see everything like rocking around. But truth to be said, that's nothing. You're just talking about 5 millimeters here, which is literally nothing. But you can see this rocking around because the displacement is being amplified by, I don't know, 1000 or something. So basically, that's it. I think that we have finished something called time history analysis. Just to make sure one thing, if you take a look on the static force, you can see that the deflection of the static force is 2.5 millimeters, whereas the dynamics has a maximum of, let's take a look, now 3.37. Okay, we are having some more vibrations, which means that we have some sort of resonance, but not really that resonance. We have a higher harmonics resonance, and that's why it's not really amplifying a lot. It's just a little bit over the static analysis, but it's a long story. I think I'm done with this. Lucky you, you didn't have to see any of the bugs I had to fight off screen. Alright, so in the end, I hope that you enjoyed this video and it was beneficial for you. If you have enjoyed this video, please consider liking, sharing, commenting, and subscribing. It helps a lot, especially subscribing, because it increases the reach of my channel. This is the Civil Engineering Essential channel, and we will catch you in the next video. Postscript, my daughter is sleeping beside me, and that is why I'm a little bit low in volume. But relax, everything is fine with me. I'm not ill or anything. Thank you very much. See you next time.